All right, so what we've done so far is we've covered, just making sure it's recording, yeah. We've covered a lot of material so far. We're still going to go through this week. We're going to do projectile motion, which is really kind of an extension of the Thursday lecture. We're going to, in the next two lectures after this, talk about the other two coordinate systems. So there's some important concepts that will come out of this one that I'll sort of highlight as we go through. But what we've done is define position, velocity, acceleration, curvilinear motion, Cartesian coordinates, and now we're in section 2.4, which is really still xy, but it's projectile motion as a specific item. So we have position, and if you look last week, I had all sorts of forms of it. I'm just going to write a very simple form of it to start for all three of these. So position xi, yj, zk, velocity vxi, vyj, vzk, and finally acceleration, which equals axi plus ayj plus azk. And really the whole point of all of these coordinate systems is to get away from trying to describe the full motion. I want to describe things in a simpler way, and the simpler way is that if I have a velocity vector, I can say vx, vy, vz, and then sort of do some sort of manipulation or calculation on those. Oops. So there are a lot of different examples of this, but the big important point of all of this, and we've talked again about this to a certain degree, is that horizontal motion has no acceleration in this course. Ax is equal to 0. Ay is equal to g, and g is pointing downwards. And dependent on your coordinate system, g is going to have different magnitudes. Projectile motion can be treated as two rectilinear motions, one in the horizontal direction without acceleration, one in the vertical direction with acceleration, and that's gravity. So here I have two balls, one that's dropping down and one that has a small horizontal velocity that is imparted before it drops. Now one of the things, and each of those images is taken at the same time. So this image right here is taken at the same time, so of course T1, T2. You'll notice it drops at the same rate, but it moves out at a constant rate. So the yellow ball is moving at a constant rate. Can you sit down? The yellow ball is moving at a constant rate to the right. Now, this is kind of useful to sort of recognize and remember, because every other coordinate system you're ever going to deal with, we're going to keep to that same sort of condition. We don't have rockets that impart energy. Now, the other thing that I think is actually kind of neat, if you look on YouTube, you certainly can find it, is the bullet case from Mythbusters, which was exactly this. That is, they took a bullet and they fired it, and then they dropped it at a certain point, and at the same time they dropped one at the location, the X location, and they showed that the bullet dropped at the same rate in both cases. And it's kind of a neat experiment to convince yourself that this is right, and the other thing is that it helps you be convinced that it is worthwhile to do this sort of assumption. So we have a whole bunch of assumptions we're making here, but the big one is that is acceleration in x be equal to 0 reasonable? Projectile motion is when an object flies in the air. It has a curved path. It's parabolic. You know that because you've got an x squared equation or a y squared equation. It has a curved path that changes with speed, angle, and height. We can use math to find this path. So if I have a basketball, it's going to follow this curved path. And as it follows this curved path, it will have a vertical direction and a horizontal direction, but only one acceleration. Uh-oh. Ah. So the acceleration in the horizontal direction is going to be 0. The acceleration in the vertical direction is going to be g. I'm just going to change my thing. But nothing really changed here. We still have the same governing equations. We just have this very particular case. And the reason why we kind of fixate on projectile motion is that primarily one of the reasons why engineers exist is so that we could blow up castle walls. So we had to know when to put the rock into the wall. We've become useful for other things since then. So you kind of have these basic relationships that occur, and the important quantity here in all coordinate directions is this AC. So in the x direction, it's just 0. In the y direction, it's g downwards. And every problem that you could face can be solved with this. Which kind of leads to this picture. This picture is the first step, and I'll come back to this later, in fact in the next lecture. I have a particle. I give it an initial velocity v naught. It's going to have a v naught y and a v naught x. So v naught x never changes in my problems. V naught y, on the other hand, does. As this thing sort of rotates or moves through its path, I will have vx, vy, and as it gets to the very top of its flight, vy is equal to 0. And you'll notice that the vy is the only term that changes in terms of direction or magnitude. That is, vy starts out at some value, it decreases until it reaches 0, and then it starts increasing in the negative sense and reaches the bottom at the same velocity, by the way, vy. Vx, on the other hand, never changes. And one of the other things that you have to realize and remember is that in all of the coordinate systems, the total acceleration never changes. And this is important because we're going to start looking at problems next time in NT coordinates where acceleration in the tangential and normal direction do vary, but the total value is always going to be g if it's, say, a projectile motion. Any questions about this so far?
Are there any cases or examples where Vx does change?
Most cases in reality should. So if I have a slow-moving large object that I fling in the air, say a refrigerator, if I do that, I'm going to have an air resistance that occurs, and that will cause a slowdown. So air friction drag, and that's what I do for a living outside of this, it will play a role. But surprisingly, the assumption of an AX equal to 0 is actually not bad for most cases. Any other questions? All right, so let's do some practical cases. Oh, I misordered things. So I'm going to do two cases which are basically the same. I'm going to show the same figure in both cases. But I'm going to change some numbers in the second case, and I do it just because it makes my life easier. I have a ball that is located 1.5 meters up. I have defined on that figure an xy coordinate, so a 0 location. The v naught is at an angle of 3 degrees with respect to the horizontal, so right here. V naught, 3 degrees. G is acting downwards, no surprise, and that again is going to be the only term that I worry about. I'm told that at the end of its flight, y final is 0.97 meters. So it starts out at a high point, it moves through an arc, and as it comes back down, it's going to get to 0.97 meters. So all of these problems start out the same way. Acceleration in x is equal to 0. And hit Vx is equal to V naught cos 3 degrees. And I know it's cos 3 degrees because that is my V naught x, that is my V naught y. V naught x then is going to be V naught cos 3 degrees, and I know that that value will not change with time. It will stay the same throughout this motion. I didn't highlight this before, but there's a distance of 6 meters from left to right. So x is equal to 6 meters, which equals x naught plus v naught x times time plus 1/2 axt squared. So a couple things here. I'm not rederiving this relationship. I'm assuming constant acceleration, and that's a reasonable assumption here because I mean, it's projectile motion. I haven't done any types of simplification. I know this distance, this final distance is 6 meters from the initial point. I know the way I've defined this also, that x is equal to 0 to start. So in that case, why isn't it not doing that? So x naught is equal to 0, ax is equal to 0 because there's no acceleration in the x direction. So time is equal to 6 meters over V naught cos of 3 degrees. So now I have the time it takes for the ball to traverse the 6 meters. Now, the time it takes to go up and down to 0.97 meters, because what I want at the end is to calculate xf equals 6 meters, yf is equal to 0.97 meters. Everything is defined with respect to the ground. So I've defined the ground as 0. I start out with a y naught of 1.5 meters. I end with a y final of 0.97 meters. So if I do that, I have y equals to y naught plus v naught yt plus 1/2 ayt squared. V naught y is v naught sine of 3 degrees. So the initial velocity of the projectile, of the ball, is v naught sine 3 degrees. And I get that from my triangle over here. So my final position, my initial position, my and you'll notice again that I have not written minus 1/2 gt. I just wrote it as 1/2 gt squared, and later on I'll turn this into negative 9.81. So if I do that, I have 0.97 meters, final location, 1.5 meters, and I know the time it takes because that's the time I just solved for at the top of the problem. So, now, if I look at my units, which I should do at all times, and I can do that right now, I have y, which is in units of meters, y naught, which is in units of meters. I have v naught, which is meters per second times seconds, so units of meters. And here, meters per second squared times second squared meters. So all of my units do stay consistent and correct as I'm solving this problem. So now I end up with a quadratic equation. I'll end up with cos squared on the bottom, on the last term, cos on the bottom here, and then 0.97 minus 1.5. substituting all the terms in, I get V naught equal to 14.5 meters per second. There are a lot of different ways to solve this problem. I certainly encourage you to use some computer algebra if you can. It makes it a lot easier. Any questions?
So it's like the basis of projectile motion problems is using one direction to solve the time, and then that carries over to the other direction.
Exactly. So for example, in this case, I just wanted to know when the particle was going to be at the final position. So if it's going to be at the final position, x takes that long to get there, and y takes that long to get there. So x and y then have to be at the same position. You're going to see a lot of these problems. They're not that bad. Make sure that when you set them up, you just recognize, first of all, constant acceleration, and where they get kind of messy is problems like this, where I decided to do kind of a variant on this problem. And a variant on this problem is just this one right here, which is, again, projectile motion, different numbers. Oh, okay, sorry, I didn't copy that over. 10 meters. So, same sort of problem, I just changed some numbers. But you can see that as far as the drawing is concerned, it's exactly the same drawing. It's something happening. But you're asked to find something a little bit different here. You're asked to find the xy location of the maximum height of the throw. Now again, one of the important steps you take when you solve these problems is defining your coordinate system. Now that's not expertly drawn by me, but it should be coincident with the ground, and xy is sort of the floor. So 10 meters is measured above the floor, 10 meters per second at 20 degrees, and you have gravity that is 9.81 meters per second squared. This bit right here is not important, and I'm just too lazy to change the figure. So what you're asked for is where exactly does it reach its maximum height? And this is a variation that's kind of interesting because you really should know what it is, because we talked about it just 5 minutes ago, 10 minutes ago. So one thing that I know is that at the maximum height, at the maximum height, Vy is equal to 0. So remember, it can't go up any higher because it has a vertical velocity of 0 at the top. So after that, the acceleration, the gravity, is going to act to push it down. So Vy is equal to 0 at the top, but Vx doesn't change. So it's moved to the right, and it keeps moving to the right, but it has reached the top, the peak of its motion. So if I put down my numbers, I have g, which is acting downwards. I have, no, I don't need to do that, minus v naught yt, which equals, or v naught y, I'm thinking of something else, gt. But g is negative, so I'm not going to get a weird number, or a weird time. So time is equal to v naught divided by magnitude of g, which yields 0.35 seconds. So if I know it's 0.35 seconds to get to 0, I know how long it takes to get to the peak. Acceleration of x is equal to 0. Vx equals v naught x, which equals v naught cos of 30, or sorry, not 30, 20 degrees. So the moment that the ball is at the highest point of its flight, it's traveled to the right a distance of 0.328 meters. And I can calculate from that, and I will obtain that y final is 10.6 meters. So the xy location of the peak is going to be 3.28, comma 10.6. Again, you just have to remember that you want everything to occur at the exact same place. Go ahead. It's supposed to be cos 20. I wrote this problem with a different value to start, and I forgot to update that. Thank you. Any other questions on that? Go ahead. So V naught y, oh yeah, it's V naught y. Because what I've done, not very expertly, is say 0 equals to V naught y plus gt. Then I'm going to say minus V naught y equals gt, but then recognize that minus V naught y equals minus 9.81 t. From there, that I get rid of the sign. I wrote it as variables because I like variables better, and I make less mistakes with variables. And then I feed that into that right there. Oh, actually, right into that right there. Any other questions on that? Go ahead.
Did you also solve for the y direction by doing df squared equals vi squared?
You can. Okay, so I did it, and it's horrible. It's absolutely horrible, and the reason why it's horrible is that you need to carry about 8 significant digits. So if you solve for it and you carry, say, 2 significant digits, you end up with a number that is off. If you carry 4, you get closer. If you carry 8, it works out super. So that was, I ended up sort of beating my head against that wall also. Any other questions on it? You can use either one of the approaches, but generally if you're solving for time, just use this approach. If you're solving for position, use the other. again, one of the challenging sort of problems that we have in this course end up not because the motion is complex, it's because the geometry ends up being a little bit confusing. And so, just as a reminder, hopefully Wednesday next week I will be able to put out the first set of notes and for this year, and I will have all of them together. I haven't been able to do that. Okay. I have small packages traveling on a conveyor belt, and they fall off onto a 0.75 meter long loading car. If the conveyor is running at a constant speed of velocity of the conveyor, 3 meters per second, determine the smallest and largest distance r at which the end of the car can be placed so that the conveyor, or can be placed from the conveyor so that the packages enter the car. We worry a lot about boxes falling into carts. So if we go down that road, you'll notice that this time I have defined the coordinate system. And the coordinate system is acting downwards. So y is positive down. That starts out at the upper left corner here as 0, 0. And I'm just going to erase this because I think this will get confusing if I leave it there. The block, or the box, is dropping a distance of 2.5 meters, which is a positive distance in this coordinate system. And the other thing I should sort of point out is this 35 degrees right here. That may not be clear. So with respect to the horizontal, it's a counterclockwise 35 degrees. So up. A and B are the two ends of the cart. You're going to spend a lot of time sort of doing these sorts of geometries. Please make sure that you spend time practicing and getting out all of these, or being able to do this kind of separation. And hopefully you write better than I do. So V naught sine 35 is your Vy, and it's acting, V naught y is acting down. So my y final is 2.5 meters. My starting point is 0 meters. V naught sine of 35 degrees plus 1/2 g t squared. 2.5 meters equals 0 meters plus V naught t sine 35 degrees t plus 1/2 9.81 meters per second squared t squared. Okay. So the important point here is that because of the way I've defined the coordinate system, and I will keep doing this throughout the course because it's easier for me to define it in a way that's in the direction of motion, this value is positive. So pointing downwards is positive, therefore this is positive. So I end up with a quadratic equation, 4.905 t squared plus 3t minus 2.5. Okay. And t is equal to 0.5597 or negative 0.91 seconds. And you're going to get a lot of results like this. You're going to get results that are negative time. Because we're engineers, negative time doesn't exist. If you're in calculus, maybe that's okay. And so that answer is considered not practical. Is it 3 meters per second? Sorry, let me just check one thing. Yep, sorry. Again, too excited. Thank you. So if you solve through, you end up with 0.56 seconds for the time that it takes to reach that 2.5 meters. But you're not asked for that. You're asked for the total, or the possible sort of distances are where you can either hit A or B, essentially. And at some point, I'll stop writing any type of acceleration in the x direction. I'll just write Vx equal, or x equals x naught plus v naught xt. But for now, I'm just keeping it there. Oh, hold on. One day in the future, if you're in mechanical, you can do a capstone course or a capstone project with me, but not this year. All right, so x equals v naught x plus or v naught xt, and r equals to v naught. Well, I'm just going to actually say r. So r is equal to the final destination. So r is equal to v naught x cos 35t, r1 is equal to 1.38 meters. R2 is equal to R1 minus the cart length. And that will equal 0.625. So you can have a distance of either 0.63 meters or 1.38 meters, and the box will fall into the cart. And we often do this just to sort of say, okay, look, the box can fall in on this end or on this end. And so if you want to cover all of those distances, and I'll put that into the figure, you either want it to hit here or you want it to hit in B. Any questions on this? This is kind of like that Jaguar problem from last week where Jaguar is sort of jumping at an angle with respect to the ground. Okay. All right. Ski jump. Do ski jump. You know, kind of like this problem, and I mean, it's not terribly complex, but maybe I want to sort of stress one thing. And I know a lot of you are very good with your calculators. I'm terrible with a calculator. I have not used a calculator in 20, 30, 40 years, okay? There are a lot of different options out there. This is a relatively simple one. It's similar to, or a problem similar to what we've done before. I have a ball A, which is thrown upwards from the top of a 30-meter building. So that's A. Ball B is thrown at the same instant at 20 meters per second. So two people are sort of throwing balls vertically up. It's kind of interesting. It's not really a projectile problem, but what point do the two balls pass? So when do they come to their matching point? And you can see that that matching point occurs somewhere in between. So I'm going to define an origin with respect to the person throwing the ball at the top. And the person at the very bottom is negative 30 meters down. So for A, SA equals S naught A plus V naught A T plus 1/2 GT squared. B has exactly the same relationship with different numbers. The trick here is to keep a consistent coordinate system. So because I've defined this as 0, this one starts at minus 30, this one starts at 0. Oh, we should just erase that. That's not really important. Okay, so I have two relationships, one for the motion of ball A, one for the motion of ball B. I can set both of them equal to each other, and the first thing I see is that both of them have a 1/2 GT squared term. I also know that my A is the same, or is 0. So that's my relationship. And what I'll find when I solve this is t is equal to 2 seconds. You'll find that they meet at minus 9.62 meters. So you have both of them going up and down, sort of hitting at the same location at the end. The reason I like this problem is that it's not, again, not terribly exciting, but I do kind of want you to start looking at computer algebra because of this. Because one of the problems, one of the challenges in this course is making sure that you keep up to date with all of your units. So problems like this are not bad. Okay, we're dealing with meters per second, meters, whatever it is. It's never going to be that difficult. You can probably do it in your head, but if you start doing it now, when you start dealing with problems with newtons and newtons per centimeter or newton, whatever it is, you're able to keep up and you can define all the terms right from the beginning. It also reinforces the idea that a calculation is not correct until the unit is correct. So if I ended up sort of solving this problem and I wrote in there 9.62 meters, or 9.62, that's wrong. It's wrong because it doesn't have any units, it doesn't have any value. So there you go. That's really all I wanted to say, other than, I didn't want to say any more. Units are one of your big challenges. We inevitably have, and I will repeat this, we do not put any English units on an exam, but we can put it into a homework or into the notes. And the reason why it's kind of useful is that English units are absolutely nuts. Okay, I can't figure them out sometimes. I know I can't figure them out if I don't do something like this. So keeping control and understanding that 32.1 feet per second squared is gravitational acceleration, and it's not 9.81 meters per second squared if you have English units. Any questions on that? That one's just there to talk about. Now the other one I ended up using too was MathCAD. MathCAD is great. The only problem with MathCAD is that you don't get all the features. SMath Desktop, the one I end up using, is free, and so it's great to use for that reason. Okay. Oh yeah, I can do this one. So this is very similar to the Jaguar problem. I've got a skier who's jumping from a ramp. The tricky bit here is that the ramp is separated vertically from this hill by 4 meters. So the skier is jumping up at a height of 4 meters above the ramp, jumps down the ramp, and leaves the ramp at 25 degrees, hits the slope at B. What is the skier's initial speed, V sub A? You've got the coordinate system. Oh boy, it's going to be one of those days. So I have A here, I have B here. I can separate it out into XB and YB. I'm also given a typical case, which is 3, 4, 5 triangles. So sometimes we won't give you an angle. We'll just say 3, 4, and 5. You should be able to calculate everything from that. Time AB equals 4/5. Times 100 meters divided by VA cos of 25 degrees, which equals 88.27 V sub A. Y sub B equals Y sub A, V naught Y, T A B minus 1/2 G T A B. Substitute in, substitute in for T, solve through the quadratic, and we are done with the lecture today with 19.42 meters per second. And tomorrow we'll talk about NT coordinates, where we'll go back a little bit and look at these projectile motions again. Thank you very much. See you tomorrow, or see you Wednesday.
So could you just go like the second ball problem to see like how you got the y coordinate?
This one, sorry. Which one?
So at the bottom, if you got the